Let us start with experiment. This is our fourth experiment. Heat transfer through natural convection. Aim to determine the natural heat transfer coefficient H from the surface of the tube in vertical, inclined and horizontal position. These are the specifications. The diameter of the tube is 38 mm. Length of the tube is 500 mm. So here also you can see some best exam practical applications of convective heat transfer. Here also you can see the difference between pre-convection and forced convection. Here air is freely moving. Here air is moving with with an external force. The heat is going to transfer from hot egg to the air here with the help of fan, but here naturally air is moving and it is carrying the heat. Again heat is transferring here, that is natural convection. Okay, so now this is the tube what we are going to consider. Now this is our experimental test setup what we have in our laboratory. First I will name the parts of the experimental setup. First one is the switch, power switch. Second one is the temperature indicator. Second one is the heat input. Second one is the heat input. Third one is the temperature indicator. Fourth one is the voltage and ammeter reading. Fifth one is the electrical heater. Sixth one is the protector. Seventh is the glass chamber. And eighth is the tube. Okay, inside the tube there is an electrical resistance coil is there. Resistance heater is there. Okay, so now, and it has a diameter d. Okay, so now air is freely moving over the surface of the tube. Okay, so this is about what experimental test setup. Then how to conduct the experiment? Just to switch on the button. Okay, so give the heat, so switch on the heater and give the some amount of heat. Okay, by setting the voltage and ammeter reading as you want. So later you have to leave it again 20 to 30 minutes. After the 20 to 30 minutes you have to take the readings here now. So here what happens, here is a air chamber. Okay, there is a gap. Air will come here and it will enter, because after 30 minutes this tube gets heated. Okay, because you have supplied some amount of heat. So what will happen after 30 minutes, the tube gets heated. Now air will come and interact with the tube and it will come out. So when the air is come out, that will becomes hot air actually. Okay, so now this is the working principle. Then what are the readings you have to take, then I will tell you. This is schematic view of the experimental setup, the experimental test setup what we have. Okay, so now this is the air chamber and there is a tube. On the surface of the tube we have placed 4 thermocouples, that is T2, T3, T4 and T5. Whereas T1, that is thermocouple 1, is placed in the air chamber. That will indicates the air temperature or ambient temperature. Okay, so now that tube can be oriented vertically, horizontally or with an angle, that is inclined. So that can be done. Okay, as I told you, there are 4 thermocouples on the tube and 1 is outside the tube. That means what, it is placed in the air chamber. Here is an electrical heater. So this is the general common nomenclature for all the orientations. Okay, so now it is vertical position, now it is horizontal position, now the tube is inclined at certain angle. Okay, again the temperatures are remain same, 4 on tube, 1 on air chamber. Okay, so now we will do vertical position and we will do inclined position. Okay, so now first I will start with the tabular column. First one, vertical component, is it right? You have to take the T1 represents what, ambient air temperature, where you have to take by rotating this knob. By rotating this knob you can take the T1. You will get the T1 reading here, temperature indicator. T1 is equal to how much you have to write. T2 is equal to how much you have to write. T3, T4, T5, you have to up to T5 you have to take the readings here now. What is T1? T1 here you can see T1 represents what, ambient air temperature, that is 39.9. T2 represents 73.5, that is T2 here 73.5. T3 is 70, T4 is 71, T5 is 70.3. So as I told you initially, what you have done to heat this tube, what you have done, you have set the voltage and current, right? What is the voltage, what is the current, you have to note down. So the voltage and current is, the set voltage and current is 60 and 0.06 ampere. So now you got 5 temperature readings and two heater reading, that is voltage and ampere you have taken. So with help of this data you can calculate the convective heat transfer coefficient. How it is, then you can see now. Average temperature. Average temperature is nothing but what? This is average temperature of the tube. Average surface temperature of the tube. On the surface of the tube, there are 4 thermocouples, T2 plus T3 plus T4 plus T5 divided by 4. You will get an average surface temperature. That is, average temperature is 82.67 degrees Celsius. Whereas ambient temperature is, you can see here, ambient temperature 31.4 degrees Celsius. Okay. After this, you have to calculate the film temperature. What is the film temperature? Film temperature is represented as a TF. The TF is equal to T average plus TA divided by 2. So now substitute T average already calculated here. T A you already know. Substitute here, you will get the film temperature as 57 degrees Celsius. So now after this, what you have to do? You have to take the properties of the air at film temperature. At film temperature means what? 57 degrees Celsius. What is it? What is the density of air at 57 degrees Celsius? That you have to take it. You have to take from the data handbook of phase number 34. That is, density is equal to 1.07 kg per meter cube. Kinematic viscosity nu is equal to 18.66 into 10 to the power of minus 6. Whereas Prandtl number 0.696. Thermal conductivity of air is equal to 0.02875 watt per meter Kelvin. These are the properties are taken from the data handbook at phase number 34. Okay, after this you have to calculate the Grashof number. What is the Grashof number? What is the equation for the Grashof number? Again, you refer to page number 112 in your data handbook. You will get in a Grashof number equation. What is that? G into beta into delta T L cube divided by nu square kinematic viscosity. Where G is 9.81, beta is nothing but what? That is 1 divided by TF plus 273. Then you will get 3.03 into 10 to the power of minus 3 per Kelvin. Okay, so now that is a beta. What is delta T? Delta T is nothing but what? Change in temperature. What is the change in temperature? That is, delta T is equal to T average minus TA. So now you know the delta T also. What is L? L is nothing but what? Length of the pipe. Length of the pipe is, already we know that is 500 mm. That is 0.5 meter. Okay. Now this is what? Kinematic viscosity. Kinematic viscosity of air, already you have taken it from the data handbook. Now you know all the values. Substitute in this equation and get the value. So now 9.81, beta is 3.0 into 10 to the power of minus 3. Delta T is 82.67 minus 331.4 minus L cube 0.5. That is 0.5 is our pipe length. Okay, or tube length 0.5 into 10 to the power of 3 divided by kinematic viscosity. Kinematic viscosity is 18.66 into 10 to the power of minus 6 to the whole square. Then you do the calculations. You will get a Grashof number as 546.86 into 10 to the power of 6. Okay, this is the Grashof number. Similarly, you have to calculate the Nusselt number also. What is Nusselt number? That Nusselt number you can get it from the data handbook. That is phase number 138. That is, Nu is equal to C into GR into PR into GR into PR to the power of M to whole bracket to the power of M. So whenever you will multiply GR into PR, right, from the data handbook for this GR into PR value, you will get C and M value. C is equal to 0.48, multiply GR into PR, you will get one value. For that value, you can get C and M constant from the data handbook. For my reading, I got it here. C is equal to 0.48, M is equal to 0.25. Then substitute here now. Then substitute, what will happen? So substitute values here now. C is equal to 0.48, GR is this much, PR is already calculated, substitute, and M is 0.25. Substitute, you will get Nusselt number as 67.06. Okay, this is Nusselt number. With help of this Nusselt number, I can calculate the heat transfer coefficient theoretically. Then what is the equation? Theoretical, you can see here now. HT is equal to Nu into K divided by L. If it is a vertical, you have to take a length here now. Okay, so now that is Nu is equal to 67.06, whereas K is thermal conductivity of air, already you have taken it here. Substitute, then divided by L. L is nothing but pipe length, already we know, that is 0.5. Substitute, you will get HT is equal to 3.85 meter square per meter square Kelvin. Okay, that is meter square watt per meter square Kelvin. Okay, so now I got HT is equal to 3.85 watt per meter square Kelvin. After this, we have to calculate the surface area. Here we are going to consider surface area because the heat is going to transfer over the surface of the tube. For that purpose, we are considering a surface area. That is capital A is equal to 5 into D into L. 5 D 0.38 meter, 5 diameter. Okay, the tube diameter. Length is the length of the tube. Substitute, you will get an area, that area is equal to 0.059 meter square. That is the area. After this, heat input can also be calculated because you have set it here, right? Because you have set it voltage and current here, right? With help of this voltage and current, I can calculate the heat. How I can calculate? We have an equation, that is Q is equal to V into I, voltage into current. Okay, what is the voltage? 60. What is the current we have set it? That is 0.06. Then multiply, you will get 3.6 watt. This is nothing but what? Heat input. Sorry, heat input, that is Q is equal to 3.6 watt. Okay, so now I will move towards practical heat transfer coefficient. This is what theoretically I have calculated. Theoretical means what? With the help of Nusselt equation, with the help of this theoretical equation, I have calculated the heat transfer coefficient. But if I want to calculate convective transfer coefficient by practically, I have to use this equation. That is Newton's equation. That is HP is equal to Q divided by A into T average minus TA. Q already you calculated 3.6 here now. Whereas A is nothing but what? A is nothing but what? Area already calculated here, surface area, fine. Next multiply T average. T average is already you know it. It is 2.67 minus, next, what is the next TA? TA is nothing but what? 31.4. Instead of 35, you have to substitute here 31.4. Then you calculate, then you will get 1.176 as the practical heat transfer coefficient. That is 1.176 watt per meter square degree Celsius, the practical heat transfer coefficient. At the end, you have to write the results. Results are convective heat transfer coefficient by practical approach is 1.176 watt per meter square degree Celsius. By theoretical approach, it is 3.85 watt per meter square degree Celsius.